So chapter 2 is all about atoms and the periodic table. We'll be going over what atoms are, what they look like. We'll also be going over the periodic table and how you use it to understand information about the different types of elements that we can find in chemistry. So when we are looking at elements, an element is a pure substance that cannot be broken down into simpler substances by chemical reactions. So it's basically something that you cannot break down. You can't make it smaller. You can't get down to anything simpler than the element itself. So examples of elements would be carbon, oxygen, nitrogen, uranium, xenon, iron. All of those are different types of elements. And in there, if they're by themselves in their own form, they can't be broken down into anything else. Each element has a 1 or 2 letter symbol. So if you look on the periodic table, you're going to see something like a box. And this box will have a letter in it, like C for carbon. The C is the symbol for carbon. And you're going to see that for different elements will have the different letters, basically showing you what that element is. Sometimes it's based on their English name and sometimes it's based on a Latin name. So the letters don't always line up with the name of the element. The elements are arranged on the periodic table, which we'll look at in a second. And this is a visual representation of all of the elements and kind of how they relate to each other. It includes a lot of information about each element. And we'll look at that in a second. So here's the periodic table of elements. If you look, you can see, so let's look at here, we see the hydrogen box. This box here is the same as this box over here, the hydrogen box over here. It's just bigger. So in this box, we have a couple different things. First, we have the atomic number, which is this number 1. Hydrogen is the first element. So it's atomic number 1. It also has the symbol H. So whenever you see H, you're going to be thinking of hydrogen. It has the name of the element, hydrogen in this case, and then it has atomic weight. This is basically how much mass this particular element has. Now we have different elements here: boron, phosphorus, tellurium, silver. If you notice this one, silver, its symbol is Ag. That corresponds with a Latin name for silver. So it's not the same, doesn't have the same letters as what's in its name. But you can see that for each of these, they all have a number, which is their atomic number. We'll talk about what that means in a second. And they also have an atomic weight. So there's numbers on here that correspond to different things. There's also numbers at the top of each column that basically group these particular elements in the column together. So like this is group 1. This is group 2, group 18. Okay, so these different elements in this particular column all have similar characteristics, so that's why they're grouped together in the column. So on the periodic table, we have different types of elements. We group our elements into different groups. So we have metals, nonmetals, and metalloids. And these different types of elements react and function in different ways. So the metals are all going to be metal-like. So they're usually shiny, they conduct energy or conduct electricity, they are usually solid at room temperature. And we've got a lot of those that we'll look at. We have nonmetals, which are basically the opposite. They're usually not solid at room temperature, but they can be. They don't conduct electricity. They are oftentimes gases, but they could also be liquids. at room temperature. And then we have the metalloids, which are basically somewhere in between a metal and a non-metal. We can break these elements down further into these different types, building blocks, macronutrients, and micronutrients that we find in the human body. So our building block elements, these four right here, oxygen, carbon, hydrogen, and nitrogen, these are found in our bodies in high amounts. Most of our body is made up of these four things. Most of the molecules that are making up your body, your physical structure, are from these four elements. We have major minerals, also called macronutrients: potassium, sodium, chlorine, magnesium, sulfur, calcium, phosphorus. All of these are found in our bodies in small amounts, but we need them in our daily diet in order to survive. We also have these trace elements, also known as micronutrients. So things like boron, iron, selenium, zinc. Again, these are found in teeny tiny quantities, less than 15 milligrams in our body or in our daily diet that we need each day, but they are necessary. So there's things that we need, but we just need them in teeny tiny amounts. So when we're looking at the periodic table, we can break the periodic table up into groups or into groupings of elements that behave similarly. So if you look at the rows, which are the ones that go side to side, so they go across, those can be groups of elements. We call those periods. So if you look at your periodic table of elements that you can find in your book, it's at the very beginning of your book, you're going to see that the elements are grouped by number for period. So we've got period 1 is helium and hydrogen. And then you go down another row, and that's period 2, which is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And you can group each of these different ones in the periodic table by period. We can also group them by group. This would be a column. So a column goes up and down. So if you looked at the last column in the periodic table, these are the noble gases: helium, neon, argon, krypton, xenon. Those are the noble gases, and they all behave similarly, and they're in the same group, group 8A, also known as group 18. There's two different ways that you can group them or number them. When we're looking at the periodic table, the ones that we are going to be looking at the most in our class are the main group elements. These are the ones that are mostly used. So 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A are the ones that we're going to see the most in our book. So we're going to be using things like hydrogen, carbon, nitrogen, oxygen, chlorine. Those are the things that we're going to see a lot of in our book. That'll be the ones that we use the most. We also have the transition metal elements. These are the ones that have the B numbers, or the like 3B on the periodic table. Those we don't use as much in our book, but you might see some of them, like you'd see iron every once in a while, copper, but those are metals that we're not going to see a whole lot of, but they are important in chemistry. All the elements are important, but we won't be using those too much. And then when you look at the very bottom of the periodic table, there's two rows that are just all by themselves. These are the intertransition metal elements. These are like super heavy metals that we don't really use very often. They're sort of kind of just out there by themselves. The only one that we're really ever going to talk about in there is uranium and maybe thorium. But those elements are not terribly important for our purposes, but they are. I just want you to kind of know what they're called, the intertransition metal elements. All right, so we can also break down our elements into these different groups, group 1A, 2A, 7A, and 8A. These are the probably the most important ones that you're going to have to know. So we've got 1A, which are our alkali metals. So hydrogen, lithium, sodium, potassium. Those four elements are probably the most important of the alkali metals. We find those a lot in different types of molecules. We also have the alkaline earth metals, which is 2A, beryllium, magnesium, calcium. Those three are the most important in the alkaline earth metals for you to know. If we're looking at these two groups, they're metals, so they conduct electricity and they're solid at room temperature, but they act in similar ways to each other, and they're really reactive, so you're going to find them in a lot of different types of molecules. If we go to the other side of the periodic table and we see 7A and 8A, the halogens and the noble gases, these are also very important. Halogens are important because they are found in lots of different types of covalent bonds, which we'll talk about a little bit later. So like fluorine and chlorine and bromine, those are found in a lot of different types of elements that we'll be looking at in our course. And then we also have the noble gases, which is 8A. And these ones are really important because these are the most stable elements out there. They are very unreactive, and they're gases at room temperature, which we talked about in chapter 1, what a gas is. So they are super duper stable. They don't like to react. You're not going to find them a lot in different types of molecules, but they are really interesting in how they are so super stable. All right. So when you are looking at two or more elements that are bonded together, we would call this a compound. So when you see two or more things stuck together, that's a compound. There are different ways that we can represent compounds, and they're all shown here. You can use what we call a chemical formula, and that's where you're going to be using letters and numbers to show how many of each atom are in the particular compound or molecule that you're looking at. So for this one here, we've got CO2. It has one carbon and it has two oxygen. That little 2 down there tells you that there's 2 of the letter before it. So there's 2 oxygen in this particular molecule. CO2 is also known as carbon dioxide. So it's probably one that you're pretty familiar with. This next one we have is C6H12O6. This is glucose. It's a sugar molecule. So it has 6 carbons, 12 hydrogens, and 6 oxygens in the molecule. So one way we can do that is by looking at these formulas, the chemical formulas, and it just tells you how many of each type of atom are in the molecule. Another thing that we can use is molecular art to show what the molecules look like. So down here we've got water. So this is 1 oxygen and 2 hydrogen molecules bonded together. So this is one type of molecular art that you might see. We've got some other options over here. We've got a Fischer projection of glucose. We have a bond line formula of vitamin A. We've got the Kekuli structure for benzene. We've got a ball and stick model of methane. We've got Lewis structures. We've got all different types of ways that we can show compounds and show what they look like and how the atoms are connected or bonded together. So what's an atom? An atom is sort of it's the smallest unit that you can get to in matter. It cannot be divided, so you can't make it any smaller. There are smaller particles within an atom, but you can't break down the atom itself into smaller parts and have it still be matter. The atom itself has a nucleus, which is the center part of the atom. It's the part that has the most mass, actually. And then around the nucleus, we have this electron cloud. The electron cloud is basically anywhere that you would find an electron zooming around on the outside of the atom. There are three main types of particles that you find in an atom. We've got a proton, a neutron, and an electron. Protons and neutrons are found in the nucleus, in that center portion of the atom. Protons are positively charged particles. Neutrons are neutrally charged particles. So a proton has a positive charge, electrical charge, and a neutron has no charge, no electrical charge at all. The electrons are teeny tiny particles that almost have no mass. They have a little tiny bit, but very, very little. And these electrons are zooming around in the electron cloud. Teeny tiny little guys zooming around out here in the electron cloud, and they are negatively charged. They have a negative electrical charge on them. When we look at that box again for an element on the periodic table, let's go back to what all this stuff means. So when we're looking at this box, we've got that symbol, the letter symbol, which is the element symbol. In this case, it's O for oxygen. The element name, written out, oxygen. The atomic number, which is up here, it's the number 8 for oxygen. The atomic number is actually a really important number. It tells you two things. It tells you how many protons are in this particular atom. It also tells you how many electrons are in this particular atom. So for oxygen, there are 8 protons and 8 electrons. At the bottom, we also have the atomic weight. So for oxygen, it's 15.99999. This basically just tells you how much mass the atom has. It's not terribly important to note at the moment, but we will be talking about an atomic weight a little bit later. Now, isotopes are different kinds of the same element. So oxygen can have different numbers of neutrons in the nucleus. And depending on the number of neutrons in the nucleus, the atom will behave a little bit differently. So it could have 6 neutrons, it could have 8 neutrons, and depending on how many neutrons are there, the element will behave differently. All right. So the chemistry of an element is generally determined by the number of electrons in the atom. And electrons don't actually move freely in space. So the electron cloud is not just anywhere outside of the nucleus of the atom. The electrons occupy specific energy levels. So they're going to be in different spots around the atom depending on how much energy the electron has. The regions occupied by the electrons are called shells. They're also called principal energy levels. But we're not going to refer to them as that. We're going to call them shells. The shells are numbered 1, 2, 3, 4, 5, 6, 7, etc. Electrons in lower number shells are closer to the nucleus and have lower energy, and the ones that are further away from the nucleus are higher energy and have a higher number. So shells with larger numbers are further from the nucleus. They have a bigger volume and can hold more electrons. So when you get closer to the nucleus, there will be fewer electrons. As you get further out, there will be more electrons. All right, so when we look at the first 4 shells, first 4 of those spaces around the atom, you can see the number of electrons that can be held in each shell. So for our first shell, the one that's closest to the center of the atom, we can only have 2 electrons. In the second shell, you can have 8. The third shell can hold 18, and the fourth shell can hold 32. So as you can see, as you go out away from the nucleus, more electrons can be housed. And again, it increases energy as you get further away from the nucleus, increases the number of electrons the further you get away from the nucleus. Within each of these shells are subshells and orbitals. So we break it down further. So we have shells, we have subshells, we have orbitals. So we're breaking it down into smaller and smaller pieces. So the shells are divided into subshells. These are lettered. So the shells were numbered, the subshells are lettered, S, P, D, F. And then inside the subshells, we've got orbitals, which are even smaller spaces where you can find an electron. So an orbital is a region of space where the probability of finding an electron is high. That's where you're usually going to find the electrons. Each orbital can hold 2 electrons. And that's for every single orbital that you find within the atom. So there's 2 in an orbital. All right, so let's look at this. So inside one shell, we have 4 subshells, S, P, D, and F. And inside each subshell, we have a certain number of orbitals. So in the S subshell, we have 1 orbital. In the P subshell, there are 3 orbitals. In the D subshell, there's 5. And in the F subshell, there are 7 orbitals. For the subshells, the energy increases as you go from S to F. So S is low energy, F is high energy. All right, so if you are given the number of electrons in an atom, you can start plugging these into the electron structure and plugging these electrons into subshells and orbitals and all of that. All right, so level 1, we have 1s. So this 1s is shell number 1, subshell S. Okay, and so in shell number 1, subshell S, you can have 2 electrons because it's an S shell. So it only has 2 electrons, or it only has 1 orbital, so it only has 2 electrons. So the maximum number of electrons that you can find in the first shell is 2. Shell 2, so the second shell out from the middle of the atom, can hold 1s shell and 1s subshell and 3 p subshells. And these are labeled 2s, 2p, 2p, 2p. The number of electrons in each of these in the orbitals is 2. In the s shell, you only have 1 orbital. So you can have 2 electrons in the s shell. In the p shells, there are 3 orbitals. So there's 3 p orbitals. Each orbital holds 2 electrons. So if there's 2 electrons here, 2 electrons here, and 2 electrons here, the total number of electrons possible in the p shells is 6. Add 2 and 6 together, the maximum number of electrons that you can find in our second shell is 8. All right, when you move up to the third shell, We're looking at subshells and orbitals. We've got 3s. Remember, there's only one s shell, or one s orbital possible. For the p orbitals, we have 3 possibilities: 3p, 3p, 3p. So there's 3 different types of, or 3 orbitals in the p subshell. For d, we have 5 orbitals within the d subshell: 3d, 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 3d. If you go and look at the number of electrons possible in each of these orbitals, 3s has 2. There's only one orbital here, so there's 2 electrons that can live there. There are 3 orbitals here. Each orbital can hold 2 electrons, so there's 6 possibilities, or 6 possible electrons that can occur in the p subshell. For the d subshell, there are 5 orbitals, 2 electrons per orbital, so a total of 10 electrons that can occur in the d subshell. If you add these together, 10 plus 6 plus 2, the total number of electrons that you can find in our third shell is 18. All right. So the orbitals, or the orbitals have shapes. You're not going to need to memorize this. This is just something that I find interesting. They're shaped different. So for 1s and 2s orbitals, they're spheres. The p orbitals look like dumbbell shapes. They're kind of weird. D orbitals look different. F orbitals look different. They all have these different, like, weirdo shapes. Electron configuration describes how the electrons are arranged in the atom's orbitals. The lowest energy arrangement is called the ground state. We're going to go over how to figure out what all of this is. So there's some rules that we have to go over to determine the electron configuration of an atom. First, we're always going to place the electrons in the lowest energy orbitals, beginning with 1s. So an orbital closer to the nucleus is the lowest energy, and then within a shell, the orbital energies increase from s to f. So you always want to start with the lowest number and s. Okay, so we're starting with s, and then we go to p, then d, then f. So you always want to start with low energy. So this results in the following order: 1s, 2s, 2p, 3s, 3p, 3d, and so on. And again, each orbital holds a maximum of 2 electrons. All right, so this is the kind of fun part. You can draw one of these tables where you can put the electrons into place. Each one of these lines represents an orbital. So we've got our 1s, there's 1 orbital in the s subshell. 2s, so our second shell, only 1 subshell, or our subshell s, only 1 orbital in the s subshell. Our second shell, the p subshell, has 3 orbitals. 3 shell subshell s has 1 orbital. 3 shell subshell p has 3 orbitals. You can put 2 electrons here, 2 electrons here, 2 electrons here, 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 and here. So this table is actually pretty useful. All right, so let's look at the electron configuration for the first row elements. Let's start with hydrogen. Hydrogen has 1 electron, so its electron configuration is 1s1. So this superscript here is showing the electrons, the number of electrons within this subshell. So we've got shell number 1, subshell S, we have 1 electron in subshell S. For hydrogen, there's only 1 electron. This is the only place that you can put it. For helium, it has 2 electrons. So we're going to put both of those electrons in the first shell, subshell S, and that 2 is the number of electrons that are within that subshell. So for helium, it's 1s2. If you go to the second row of elements, we're going to start to get a little bit more complex. So for lithium, lithium has 3 electrons. So we got to do a little bit differently. So we've got 1s2, 2s1. So we've got shell number 1, subshell S has 2 electrons. Shell number 2, subshell S has 1 electron. So 2 plus 1 equals 3. So we get all 3 of our electrons are accounted for in this electron configuration. All right, carbon is 6 electrons. So it's going to look like this. 2 electrons in shell 1, subshell S. 2 electrons in shell 2, subshell S. And then 2 electrons in shell 2, subshell P. Neon has 10 electrons. It's going to look like this. 1s2, 2s2, 2p6. And if you add all the electrons together, 2 plus 2 plus 6, you get your total of 10 electrons. So we're just kind of filling this in as we go. Okay? All right, so let's talk about valence electrons. Valence electrons are those that are found in the valence shell. The valence shell is the outermost shell, or the highest energy shell for our atom. Electrons in the valence shell are called the valence electrons. So if we're looking here at beryllium, beryllium has 4 electrons. If you look at the numbers, we've got shell 1 and shell 2. Shell 2 is our highest energy shell for this particular atom. It has 2 electrons in it total. So beryllium has 2 valence electrons. These are the 2 electrons that are in the highest energy shell. Chlorine's a little different. Chlorine has a lot more electrons. Its highest energy shell is the 3 shell. Now it has electrons in the S subshell and the P subshell within our 3 shell number 3. So we have to add together all of the electrons that occur in this shell together to find out how many valence electrons are here in our chlorine atom. So 2 plus 5 equals 7. So chlorine has 7 valence electrons. Okay, so 7 valence electrons for chlorine, 2 valence electrons for beryllium. Elements of the same group have very similar electron configurations, so they're going to have the same number of valence electrons. So if you're looking at all of the atoms in group, or elements in group 1, they're going to have the same number of valence electrons. Now, what's really cool, the group number equals the number of valence electrons in the A groups. So group 1A has 1 valence electron. Group 2A has 2 valence electrons. Group 3A has 3 valence electrons. Group 4A has 4 valence electrons, and so on. So that's kind of a cool and easy way to remember how many valence electrons you have for those groups, the A groups. The other ones are a little bit different. Obviously, the exception is helium. It's in group 8A. It does not have 8 valence electrons because it only has 2 electrons total. So it has 2 valence electrons. And the chemical properties of a group are similar because they have the same number of valence electrons. So because they have the same number of valence electrons, they have the same number of electrons that can do stuff on the outside of the atom. And so these atoms tend to act similarly. All right, so valence electrons for our groups are shown here. So if you look for group 1A, we've got one valence electron, one valence electron, one valence electron. For 2A, we've got 2. For 3A, we've got 3 total. 2 plus 1 is 3, right? For 8, we have group 8A, we've got 8 valence electrons. 2 plus 6 is 8. Our exception here, helium being the one that doesn't follow the rule. There's always one. All right, so we can represent our valence electrons in a visual way. We can use this using electron dot symbols. Dots representing the valence electron are placed on 4 sides of the element symbol. Remember, the element symbol is just a letter or 2 letters that represent that element. Each dot is just 1 electron, and if you have 1 to 4 electrons, you're going to use just individual dots. If there's more than 4, you're going to start to pair them. So let's look at some examples here. So element H, C, O, and Cl. So these are hydrogen, carbon, oxygen, and chlorine. The number of valence electrons for each of these are shown here. So we have 1 valence electron for hydrogen, 4 for carbon, 6 for oxygen, and 7 for chlorine. And these are the electron dot symbols that you would draw for each of these. So for hydrogen, we have 1 electron. So we just have 1 little baby electron shown here. For carbon, we have 4. So there, since it's 4 or less, we do them as individuals. 1, 2, 3, 4 on the 4 sides of the C. Oxygen has 6, so we're going to do some of them in pairs. You start by doing 1, 2, 3, 4 around the edges, and then you add the extras in pairs. So we have 6, so we have to add 1, 2 as pairs. For chlorine, it has 7, and so we're going to do pairs here as well. So 1, 2, 3, 4, and then you add the extra 1, 2, 3 in pairs. So we've got 7 total around our chlorine for our valence electrons. All right, here's some more interesting information about our periodic table. The size of the atoms increases down a column as the valence electrons are further from the nucleus. So as you go down, the atoms get bigger. The size of atoms decreases across a row as the number of protons in the nucleus increases. Basically what's happening here is as you have more protons, as it gets heavier, basically has more pull toward the center of the atom, which makes it more compact. So the atom gets smaller as you go from left to right. As you go from top to bottom, the atom gets bigger. So it doesn't seem like that's how it should be, but that's how it is. All right. Ionization energy is the energy needed to remove an electron from a neutral atom. Basically, how much energy do you need to pop an electron off of an atom that does not have a charge? Ionization energies decrease down a column as the valence electrons get further away from the positively charged nucleus. Basically, as you go down the column, it's easier to pop an electron off of the atom because they're further away from the center. Electrons are attracted to protons because they have opposite charges. Have you ever heard of opposites attract? So the negatively charged electron is attracted to the positively charged proton. If the electron is further away from that positively charged proton, you have an easier time of removing it from the atom. And ionization energies increase across a row as the number of protons increases. So the more positive charges you have, then in the center of the nucleus, the harder it is to pop an electron off of the atom.